My guest today is Professor Simon Hogg, who's Emeritus Professor of Engineering at Durham University in the UK. His research interests include power generation, turbomachinery, and wind power. Welcome, Simon.
Thank you.
Yeah, so you sent me a couple of reports on different ways to generate electricity. And one area that we want to dig a little deeper into is offshore wind. And so the report here at the beginning says the UK's offshore wind market is one of the largest and the most successful in the world, with more than 50 wind farms across the UK coastline at various stages of development, producing enough renewable energy to power half of all UK homes. The UK's offshore wind pipeline currently stands at approximately 95 gigawatts, with a government ambition to decarbonize the power system by 2030, including a radical increase in offshore wind capacity in the same time frame. Recent announcements by the UK government, including the creation of Great British Energy and its partnership with the Crown Estate, which I think is a private entity, right?
Well, the Crown Estate is a government organisation that owns it owns the seabed around the UK for one thing, which is why it's so important to the offshore wind industry.
So
basically they're responsible for leasing areas of the seabed that developers want to stick wind farms on.
Yeah, I didn't know that. So we'll talk a little bit about that. It says offer an important platform to build momentum and provide confidence to meet longer-term ambitions for offshore wind. So before we get into the sort of the policy areas and future prospects, I want to sort of get a little bit of a technical understanding. So on the surface, a wind turbine, all the wind turbines I have seen seems to have three leaves on it. Wind flows into it, it turns, and on the back end of it, it's generating electricity, right? So everybody is familiar with wind farms. It's called wind farm. We use wind energy to do some sort of mechanical thing, to crush something or bend something or something like that. It's sort of a similar concept. Here, kinetic energy of wind is transferred into electricity that could be used for a variety of purposes. Is that the way to think about it?
Yeah, I mean, traditionally, hundreds of years ago, wind power was used to power windmills. So as you just said, they were used for various purposes for grinding materials, whether that was corn or other materials as well, ground using wind power. So the energy of the wind converted into kinetic energy and used to grind things up. So what we're doing now are wind turbines. So we're not grinding anything. They're not, and so thank you for not calling them windmills. That always grates with me instantly. So you've avoided that. So these are wind turbines, and so the turbine itself, the standard design is the three-bladed, what they call the Danish design. The Danes were really led the way in the development of wind power for electricity generation, and this three-bladed. I mean, not all wind turbines you see around are three-bladed. Occasionally you'll see two-bladed ones, for example, or certainly smaller ones on farm buildings and things. But the vast majority of wind turbines that you see for power generation purposes are the three-bladed design that you've just alluded to there, with a horizontal axis. There are other types of wind turbines you'll see around with vertical axes, and there's always a big debate within the community as to whether vertical axis turbines could have technical benefits over the standard three-bladed Danish type turbine. That keeps popping up from time to time, but pretty much the three-blade horizontal axis technology has progressed to the point now where I think that's going to be the preferred solution moving forward over the next few decades. So when you put multiple turbines together, that forms your wind farm. And if you're looking to generate electricity, a coal-fired or nuclear power station will be anything from sort of 500 megawatts up to 1.5 gigawatts. This sort of scale, whereas the world's largest wind turbines now that are being installed are sort of 13, 14 megawatts, and you can actually, the Chinese have a prototype 29 megawatt wind turbine actually operating at the moment, according to what they put out on the internet. So, but they're not at the hundreds of megawatt scales. So the only way you can generate that level of power is by having lots of them, and then they become a wind farm.
Wind farm. So just to get some statistics on the UK market. So it says here, currently you power half of the domestic consumption by wind power. I understand that UK, Germany, and China are sort of the three countries who have done wind really well.
Yeah.
So half of the domestic market. So the very roughly, what's the total power consumption of UK?
Yeah. Okay, so just to pick up on a couple of points that you mentioned there before, I want to agree with you before I answer that. Yeah, the UK, we had up until about 3-4 years ago now, the UK had more offshore wind power deployed than any other country globally. Germany wasn't that far behind, UK were the leader. But then in recent years, we've been overtaken by China. So now China is number one with the most this is offshore I'm talking about. There's also onshore wind farms, but for offshore wind, the UK was the world leader and still is positioned in terms of deployment and the use of wind right at the forefront of globally of countries that use this form of low carbon energy. The national grid, or national system operator as it's now called, they put up, if you Google grid watch, there's a very interesting website, and you can actually see the UK's electricity usage on a 5-minute basis on that website. And I've got it in front of me now. I'm looking at it. So right now, as we're speaking, the total demand for the UK, so that's domestic and industry, everything, bearing in mind, you know, it's 6 p.m. UK time here, so it's not peak demand time if we think of industry. But at the moment, the total demand is about 32 gigawatts in total for the UK, and right now we're generating just over 20% of that from wind. So it's not, you know, the amount of electricity that we get from wind varies obviously during the day and over the weeks and the months, because it depends upon the wind resource that's available at the time. So 50% of the domestic power, I'm not sure of the 32 gigawatts, I'm not sure what the breakdown between domestic and industrial is for that. So I think, you know, I'm an engineer, and I don't like to talk about numbers of homes or whatever. I like to talk about gigawatts and things that I understand. So right now, 32 gigawatts is the total, and 1/5 of that is coming from our onshore and offshore wind combined, if you like. And now that number, 32 gigawatts, it actually peaks now at about 45 gigawatts. So when the most electricity is being consumed industrially and domestically in the UK, it's about 45. Those numbers are much lower than the numbers you were just quoting from that report that I shared with you earlier on. And that's because that report is looking at the requirements for 10, 20 years hence, when 2030. At the moment, we're fairly early days in the electrification of our transport system. You know, we do have electric cars here in the UK, but there's not mass uptake yet. That is coming. And similarly, we still heat a lot of homes with North Sea, with natural gas in particular, and that will be phased out, and we'll move over to heat pumps and electric heating. So the demand for electricity is going to go up significantly as we move forward over the next couple of decades from where it is now, because of the electrification of heating and transport. So that's why that number is much bigger.
Yeah, so as I mentioned, Simon, I used to be an engineer, and I forgot most of this stuff. So I want to sort of get the basis right here. So when you think about electricity, there are two metrics there. There's voltage, and there is sort of current strength measured in amperes, right? So if you multiply current by voltage, you get this sort of power metric called watts. Is that right?
Yep, that's right.
And then if I have a machine that's consuming 1 watt and it's running all year, I will have 365 multiplied by 24 watt hours. Is that the total
that's correct.
consumption?
So that's the amount. Yeah. So the watt, if you like, is the is the rate at which you use electricity. So it's what is it, basically 1 joule per second, and a joule is the amount of energy, as is a watt hour or a kilowatt hour or a megawatt hour. It's the same thing. Okay, it's a different unit, but it's the same. It's measuring the same thing as a joule. You know, it's an amount of energy. So you know, if you could capture it, the number of watt hours would be the amount of energy you've used, and the number of watts is the rate at which you're using it.
I would imagine for the UK market as a total, to make the numbers easy, it will be more like a terawatt hour of total consumption, right?
When you start looking at countries' consumptions, you're into terawatt hours. Yes,
and so you said about 20% is currently generated by wind, which is a phenomenal thing, actually. No other countries anywhere, maybe Germany and China, are close, but everywhere else it's down in the 1%, 2%.
And sometimes, but that's a fairly low percentage. This you know, the website that I mentioned a few moments ago, I'm just looking at the graphs now, and if I look over the last week or so, on Thursday last week we were generating considerably more power from the wind. So at the moment, you know, I said it's just over 20% of the 32 gigawatts. It's just under 7 gigawatts from wind right now, but we were generating more than twice that from wind on Thursday last week, for example. So that's, you know, it does vary, but that's just where we are right at this 5-minute point in time.
Yeah. So from a technical perspective, if wind doesn't come, the turbine doesn't turn, you get no energy. When there is a lot of wind, turbine turns faster. If the turbine turns faster, do you get more voltage and more intensity? How does it work?
Well, you get more power. Okay, it's the important thing is the power. You know, you're taking the power of the wind and converting it to the power of electricity. So it's the number of watts is the important thing. You can play, you know, if you're a power engineer, you can play tunes with voltages and current. You can step up one and down the other and whatever, you know. It's always the product of the two, as you've said. When you multiply them together, you get the number of watts. So it's most useful to think of the power in watts than to think of voltage or current independently. So, but I think what you're alluding to there is the variability of wind, which is you know, is one of the challenges of having. There are fundamentally two major challenges of integrating large amounts of wind into your energy system. Okay, and one of them is the obvious one, which is the power is only really there when the wind is blowing. You know, and therefore you need something else to replace it when the wind is not blowing. Yeah. Okay, and and the answer to that will be, for countries like England, that's going to have, or Great Britain that has lots of wind power, the answer is going to be large amounts of energy storage. So basically, at times of over capacity, when you're generating more wind than the grid actually needs, then you store excess electricity in one form or in one storage device or another, and then when the wind isn't blowing or isn't blowing strongly enough, you can then release that electric power back onto the grid to make up for the fact that it's not generating as much at that point in time. So there are, and already in the UK there are lots of battery storage projects around. Some now getting quite large in terms of their capacity. So storing electricity in batteries is one way of doing it. There is in Wales we have something called Dinorwic, which is one of our pumped storage facilities. So that stores it in using water. So basically, there's a mountain with a lake at the top of it and a lake at the bottom of it, and a turbine halfway between the two that will also run in reverse as a pump. And basically, in times of oversupply of electricity, they pump the water from the lake at the bottom of the hill back to the top of it, and then when they need to release that energy, then the water flows in the opposite direction, turns the turbine and generates power. So that's another way of doing it. I work with a company who are looking at compressed air energy storage now, where you do a very similar thing, but you do it by compressing air and then expanding the air through a turbine to produce the power. And then the big one that lots of people are talking about is hydrogen. So using electrolyzers to convert the electricity into hydrogen, and then you can. Hydrogen is a great. They use the word vector now to describe energy sources or energy storage devices, and hydrogen is a great vector for energy storage because it's relatively straightforward to convert it back into electricity. You can do that using a fuel cell, or you can do that by burning it in an engine and driving a generator. You can convert it into heat, obviously, by burning it, and you can use it for transport as well, either as a combustion fuel, or indeed with fuel cells in cars. And even here in the UK, there was a hydrogen powered train that was in the media a couple of years ago, quite extensively.
So of these three methods you mentioned, batteries, pump storage, and hydrogen, from an efficiency perspective, which one is preferred?
So it's not really efficiency that drives it. It's obviously cost is a big part as well. Our problem in the UK is there's only really Wales and parts of Scotland where we have the terrain that's appropriate for developing pumped storage facilities. So really that one's limited not by efficiency, but by the fact that there's there's lots of parts of England in particular where most of the people are living, and they're nowhere near geographical conditions that would allow you to do that form of storage. Okay, so batteries, you can do batteries anywhere. So they are, but there's challenges around the amount of rare earth metals that you need in order to do that. Although now people are developing, obviously there's loads of work going on to develop battery technologies that move away from requirements for rare earth metals. So we need breakthroughs there if batteries are going to play a really substantial role in energy storage. There's distributed storage though as well. So we're moving towards a situation where if we're all driving electric cars with batteries in them, your car device, could actually act as a source of electricity for your house as well. So when you plug it into your house, you have two-way energy flows. Not only can you charge your battery up, but you can also use energy from the battery domestically when you need to. So that sort of distributed storage, that's called, where people are using the cars for that purposes. That's a possibility. And then hydrogen is it depends who you talk to. There are academically, in engineering wise, in companies, industry, some people will tell you that hydrogen is the the best solution and most credible solution from that, and others will say the hydrogen ship has sailed and we don't think that's ever going to really happen. So the jury's out on that at the moment. But it's not so much the efficiency that drives it. It's your ability to, it's things like terrain, it's things like rare earth metals, it's things like the hydrogen, just storing it. If you're storing it in gaseous forms, hydrogen is about the smallest molecule that there is. It can get through anything. So it's very, very hard to actually store it for long term anyway.
Yeah, it's. I think the advantage there might be that it's transportable.
It is in the form of ammonia.
Yeah.
Yes. So that's the most stable form of hydrogen, is to convert it into ammonia, which and then you could almost drive it around by truck with the trucks running off the ammonia apart from anything else. And it's also there's a lot of interest in using ammonia in the maritime industry as well for ships. Although there are some challenges there, because when it mixes with seawater, it gets very hot and bad things happen.
So mechanically, so there's 50 wind farms again. It's producing, let's say, a lot of electricity. You have probably some sort of base load, I don't know, nuclear, that is not going to be turned off. But there could be flexible plants in the system too, like fossil fuels that you can turn off, right? And so, go ahead.
Well, so we have, so the UK has turned off all of its coal-fired power stations now. It has none of them operating anymore. So the Radcliffe-on-Soar near Nottingham was the last one to be decommissioned, and that was about a year ago now. I joined Durham University in 2010, January 2010. Before that, I actually made my living upgrading steam turbines in power stations. That was what I did. And at that time, when I joined Durham in 2010, we had 14 large coal-fired power stations, and by large I mean anything from, there was a 400 megawatt coal-fired power station very near where I am now here in in Durham called Linemouth up the northeast coast, and anything from that up to the biggest one was Drax at the end of the River Humber, which was 600 megawatt units, so 3.6 gigawatts. They've all either gone now, or interestingly, those two I've just mentioned are both still operating, but they've converted to biomass operations, so they don't burn coal anymore, they burn biomass. But all the other ones are shut down and are not coming back. They're housing estates and things like that now. They've been flattened, and the ground that they stood on has been redeveloped in some cases, at least anyway. So we don't do coal anymore in the UK. Yes, we have a fleet of aging now advanced gas cooled nuclear reactors, AGRs. There was I can't remember, it's 8 or 9 of them. That number will be wrong, but it's of that order anyway. So they are, but they're all on life extension now and still operating. There's one PWR, pressurized water reactor at Sizewell B, which is the newest nuclear unit that we have, which is about a gigawatt. But we are now building a new nuclear power station. So the first one for 30 years is Hinkley Point C in Somerset. So that one is as they all these large nuclears are, beset with challenges when you build them. And so the opening is going back and back and back, but it is now looking something like 2030 that one will come online, and that's going to be 2 1.6 gigawatt units, so another 3.2, so almost the size of Drax in Somerset. And just the other week in the spending review that the UK government has just done, they've just announced that they're also going to go ahead with another very similar development at Sizewell C. So they tend to put these new power stations in the same areas as old power stations. So that again, similar size, about another 3.2. So the UK is investing in nuclear power with these two big stations, one which is quite far down the road now of its construction, and another one which is just being given the go ahead. And there's also a lot of interest in the UK in SMRs, small modular reactors. So the challenge of the Hinkley Point Cs and the Sizewell Cs is you have to, but they're massive, and you have to build everything at site. You construct the reactor vessel, for example, at site. Whereas SMRs, small modular reactors, are much, and the clue's in the name, they're much smaller capacities, usually around 200, 300 megawatts. Rolls-Royce are actually developing an SMR that's 400.
And they don't have to be plugged into the grid, I would imagine. I mean, you can have it for a factory.
Well, you can, but they're a bit. The interest is in for grid power. So maybe repurposing some of the AGR sites when the AGR shuts down, putting 6 or so SMRs. So even though they're each at 300 megawatts, let's say, you put 6 of them on there, you've got 1.8 gigawatts. And the big advantage of them is they're modular. They're made in factories. So you bring modules to site to construct the power plant and stick the modules together to construct the power station. So you de-risk, the technical risks are much lower, and so that's seen. I personally believe that is the way forward. SMRs. One of the challenges here in the UK with it at the moment is you have to jump through the same hoops in legislation wise and in order to be able to develop an SMR than you do a big nuclear, more or less. So that needs to change. The consenting process or whatever needs to be streamlined a bit. So there are challenges there, but the technology is all possible.
And it's distributed production, so that is its own advantage. But I want to ask you sort of a tangential question. So I didn't know this. So you shut down all your coal plants over time. That's an experiment at some scale. Have you seen any health effects longitudinally?
There's nothing out there to say that since the UK shut down all its coal-fired power stations that we can really attach that to this health benefit, if you like. But they are there. I actually when I was at school, my parents lived very close to Drax power station when it was operating as a coal-fired power station, and I can remember this white Hercules used to regularly fly over the top of Drax, sampling air quality. And now whether this is true or not, I don't know. But my father told me that it was a Swedish plane, that, and because of the prevailing winds, the direction they come to the UK from the west, all of the pollution from the coal-fired stations was being blown over towards Scandinavia, and people were very worried about acid rain at the time, and it was destroying, or claimed to be destroying, forests and things in Scandinavia. And so the Swedes were taking samples and trying to build evidence of to what extent that was happening. So it's true to that extent, and those sort of things aren't happening anymore. And we know that burning coal, CO2, sulfur products, all the rest of it, it's not from a climate point of view, it's not the right thing to do anymore. And I think and we don't have to do it. We have other credible forms of electricity generation that don't do that are better, in all manner, for all manner of reasons. So I don't think, I can't give you a statistic or point you to a report. Maybe I I've not gone looking for one. I'm sure there's stuff out there, but I think just from a 30,000 foot view, it's hard to construct an argument to say that that's from an environmental point of view, stopping generating from coal is not a good thing.
Yeah, I mean, it's somewhat clear.
I mean, the problem with it is the jobs, isn't it? That's the problem. That obviously, countries that use a lot of coal for power generation, a lot of people are employed in the production of that coal in order to buy it.
Yeah.
So from a social point of view, there are implications of stopping using coal. We in this country we went through that in the 80s with Margaret Thatcher, where basically she set about dismantling the coal industry, and so that was the time then that all the jobs went. But in other countries, obviously that hasn't happened yet, and it was a difficult time here, and
we have to bring back Margaret Thatcher. So I look at, so India is a good example of this. Pretty cheap coal, a very large number of people, high pollution. It appears, I mean, I haven't seen the data, but it appears that China is rapidly moving away from it, right? So if China has overtaken UK in offshore wind, that is phenomenal.
Yeah, they are. I mean, obviously their demand is massive compared with ours. The UK is a relatively small. At the end of the day, we're 65 million people. I think we are now. We're a relatively small, densely populated country. But they are. And the Chinese, even when they're building coal, they are still operating coal-fired power stations, but the ones, they have some of the most efficient coal-fired power stations in the world, what are called ultra supercritical machines that with very high efficiencies. So even when they're burning coal, they are, because they have lots of air pollution problems as well, they're trying to do it in as efficient way as they possibly can.
So I want to talk a little bit about the Crown Estate. So the report says here the Crown Estate is an independent organization, but you said it's a governmental organization.
Well, yeah, it's I don't know what you would call it. It's a national organization that sits in London and is the consenting body. So. I mean, the clue's probably in the name. It's called the Crown Estate, so it's probably something to do with the
yes,
with the crown, basically.
Yeah, so I think it is very nicely says here, sitting between the public and private sectors, with the purpose to create lasting value for the nation from its activities. When it comes to its role in managing the seabed around England, Wales, and Northern Ireland, this means taking a holistic and long-term view of its vital resource, helping catalyze the UK's transition to net zero while playing an important role in stewarding the marine environment. So you talked about leasing the seabed. These offshore windmills.
Turbines.
Oh, sorry, offshore wind turbines. So there are multiple designs there. So I understand that the dominant design is something that you basically sort of plug into the seabed, and it operates there. But there's also floating ones, right? That seems to be sort of taking off now. And so just like the oil lease, um, when a turbine company wants to develop a farm, a wind farm, they have to actually lease the seabed from the government. Is that how it works?
Well, from the Crown Estate, yeah, yeah.
From the
So
Crown Estate.
the Crown
Okay.
Estate are actually own this the seabed in the coastal waters around the UK. So one of the great assets that the UK has is the North Sea, because the North Sea runs down the east side of the country, between Great Britain and continental Europe, and over much of its area, it's less than 50 meters deep. So it's not very deep. In fact, right now, Equinor, the what used to be Statoil, Scandinavian company, that they are now developing the Dogger Bank wind farm off the northeast coast here. So right now they are putting turbines in the water and commissioning that. It's going to be a gigawatt scale, or it is a gigawatt scale wind farm, massive. And the Dogger Bank, 8,000 years ago, was above water. So it's only in the last 8,000 years that the sea has covered that one. It's right in the middle of the North Sea if you look up where the sea area is. And I've heard it said, and I don't know whether this is true or not, I've heard it said, but even now, when the sea state is really rough, sometimes the seabed gets exposed on the Dogger Bank, on parts of the Dogger Bank. Anyway, but elsewhere, over large areas of the North Sea, it's less than 50 meters deep. So that's relatively straightforward to have fixed foundation turbines. Most of them, the turbines are on towers, and the tower is just piled directly into the seabed, essentially. So and up until a year and a half ago or so, the sort of unwritten rule was that 50 meters was about the limit for that sort of technology. However, the thinking on that has moved on quite significantly in recent times, because there is a realization that floating wind is further away than people had thought, stroke hoped. There are floating wind projects around the world. There is one off Scotland. Again, it's operated by Equinor, called High Wind, and that has 5 or 6 5-megawatt turbines. So it's a 30-40 megawatt wind farm. So small, certainly not gigawatt scale, but it is operating and has been for some time now. But they are, floating wind is still, projects are few and far between, and the foundation manufacturers are basically now looking at going into much deeper water than was previously the case. So there is a wind farm being developed off the Scottish coast at the moment, where they have towers going into the seabed at 58.5 meters deep. So that's that's already been designed. So and the fabricators of the towers, the depth of water and the seabed conditions determine whether you can use the tower or not. Obviously, you've got to be able to pile it into the seabed as well. But the manufacturers of the towers are investing in ever bigger machines that will allow them to roll towers of greater diameters and greater wall thicknesses. So I'm pretty sure they're convinced that 58.5 meters is not the limit, and we can go quite a bit deeper than that. So that's very exciting, because that means for the UK as well that we can use fixed foundations in other parts of the North Sea that are a bit deeper than the 50-meter stuff that's been developed already.
Yeah, so I don't know that geography that well, Simon. So so the project that Sweden is doing, the project that UK is doing, are these turbines seen from the coast? I'm thinking cosmetically.
So if you come to the UK, so the Crown Estate has done seabed leasing in what they call rounds. Okay, and round one was they just does it work at all? So they leased. We had a couple of 2 megawatt turbines off Blythe. I think those were the first. Literally 50 yards, a bit more than 50 yards, but not much more offshore. They were right there next to the town, more or less. And so that was the first round. Then round 2 was when they first got serious about it and started having wind farms of order hundreds of megawatt scale. And those ones are dotted around the UK coast, and most of those you can see from the seafront. So near us, for example, the EDF operate one at Redcar near Middlesbrough, and there you can if you stand, if you go to Middlesbrough or Redcar and you look out to sea, they're not very far off the coast at all. And there's lots of those. If you fly into London, again, you normally land at Heathrow, coming in from the east towards Heathrow because the winds normally blow from the west. And as you come over the mouth of the River Thames, there's something called the London Array there. That's a round 2 wind farm site, 650 megawatts in total. Again, all visible from the coast quite easily. So those are the round 2 ones. But now, the round 3 and beyond, those are much further out. So the Dogger Bank one that I was just talking about, you won't see any of those turbines from the coast. You have to catch a ferry and go over to Holland and drive past them if you want to have a look at them.
So how does the public feel about the visible ones? Are they okay with it, or are they complaining about it?
No, they're. I mean, people. I think a wind turbine, wouldn't I, is a beautiful thing, and I'm very happy to have the visible. There was a backlash in the UK. One of the reasons why we've got so much offshore wind is there was a public backlash in the UK about onshore wind turbines. People didn't like those. They didn't like them for visual reasons, but then also other people had issues with if you stand right next to them, you can hear a whoosh as the blades go past. They didn't like the noise that you heard when you were very close to them. Some people said they interfere with television signals, this sort of thing, and generally, but it was mainly the visual impact. And it's
in the US, Simon, we were told by a president that it's killing whales and something else.
It causes cancer.
I haven't seen any data yet, but
no, I don't think. I don't like. Well, an onshore wind turbine would struggle to kill a whale, wouldn't it? Unless it's in a zoo or something. But I don't think. I don't think that's. There are, for offshore wind turbines, there are environmental impacts, and so for both onshore and offshore, bird strikes are a possibility. Birds can be affected by collisions with the blades, for example. It's not a good thing. The other side of the coin may be if you have an offshore wind turbine on a tower with a fixed foundation, then there's something called scour, because obviously the tidal flows with the water moving past the turbine, and where the tower goes into the seabed, it scours away the seabed soils from around the base of the tower. So they learnt that fairly early on in the round 2 projects, where they were measuring the natural frequency of the turbines, and they were changing much more than expected because the anchoring in the seabed was changing. And so the solution to that is scour protection, or what you and I would call a pile of rocks. So they basically put big rocks around the base of the towers where they go into the seabed to prevent that scour from occurring and keep the things stable. And sea life, lobsters, oysters, they love that environment. So but again, you're interfering with the environment in that way. In that sense, it's promoting extra life, but you're changing balances. So it's not automatically a good thing that the lobsters love them. But there was an interesting. I have a slide that I sometimes use when I do presentations, and it's a plan view of a wind farm, where each wind turbine is shown as a disc in the sea, and then there are red lines running between them. And I ask the audience, what is this? And people think it's electricity cables or something like that, and it's not. It's a study that the University of East Anglia did, where they tracked some seals, and these are what the seals did, moving from base to base because the marine life that was there to feed upon. So you are onshore or offshore, there's an interaction with the environment. But that's true of anything you do. If you burn coal, there's an interaction with the environment. If you use nuclear, what are you going to do with the waste? There's an interaction with the environment. So nothing is there is. if there was the optimum solution that had nothing that anybody could get upset about, we'd have it, wouldn't we? It would be everywhere. So there are always these issues around anything in energy.
I'm holding out hope for fusion, Simon. When we get to zero cost energy,
Uh-huh.
then we can forget everything. But
yeah. Well, we have
just like
here at Durham University, we in our physics department, we
yeah.
have a lot of research going on, particularly in relation to the superconducting magnets that hold the plasma in fusion in certain designs of fusion reactor. Anyway, so yeah, we're similarly enthusiastic about things like fusion. But then, I talked about the coal and the fact that the coal industry in the UK in the Thatcher years was basically dismantled. However, another thing that we're doing here at Durham is if you think of what you do in a coal mine, you spend your whole time using pumps to keep water out of the mine, so that particularly so that the mines don't flood. When you disuse the mine, you turn the pumps off, and so most of the disused mines, the abandoned mines, are full of water, flooded, and they're not that deep, hundreds of meters, but the water temperature is a fairly constant couple of degrees above the average surface temperature, if you like, year round as well. So so there's a big push here at Durham University and we've actually got a demonstration project going in a garden village at a place called Seaham, just on the northeast coast here now, where they're going to use mine water as a heat source for a whole housing estate. So you basically you drive your heat pump not from the air or from a matrix under your lawn. You actually drive it from mine water that's pulled up from mines that are a few hundred meters deep. So it comes up anyway at 13, 14, 15 degrees C. And
so it's like geothermal.
Yeah, but it's not hot enough to heat your house directly. But if you then drive a heat pump from that, you've only got to, in the middle of winter, when the temperatures here in the UK is below 0 centigrade, if you've got a water resource, because it's fairly constant year round, if you've got a water resource at 14 degrees C, you're already halfway there to increasing the temperature that you need to put air into your house to heat it. So driving a heat pump from that resource is requires much less electric input than it would do if you were using an air source or a ground source heat pump where the water was from a matrix underneath the grounds of your house.
So I saw some research, Simon. I don't know the details of this. So near shore offshore wind turbines appear to have a positive effect on mitigating hurricanes. Have you seen this? It seems somewhat recent.
Yeah, I've not seen that. I would be very surprised if that is the case. I think when you start doing the calculations and you work out just how much energy there is in the wind, then and air movement in general, then the numbers are absolutely huge. And
so this simulation, I think, used something like 780 wind turbines in a very large wind farm configuration. But theoretically, it seems sort of interesting. So, I mean, in the US, we have Louisiana, we have certain places where they get devastated every year. It's a dual advantage if you can create a bunch of energy and sort of. I mean, it's not going to prevent
it is, but I would need to be convinced that was something that part of my skepticism comes from. I one of the things I used to do in my spare time for 20 years, I was a glider pilot. I flew sailplanes, and quite often you would, certainly in competitions, you would get 20 or 30 gliders going around in a thermal, so a rising column of air, all at once, all gaining height. And quite often somebody, if you're watching it on the ground, somebody would say, how much energy is that actually taking out the thermal? Can you kill the rising column of air because there's so many gliders in there? And you start looking at the numbers and you find that actually what the gliders are taking out is insignificant compared with the power in that rising column of air. And I would suspect that I would need a lot of convincing that the same wasn't true of wind farms and hurricane conditions. The question that's more often asked is, because there is certainly off the southern coast of the US, for example, there is interest in developing offshore wind farm projects there. But obviously, when hurricanes are a possibility, the question that's often asked is will the hurricane destroy the wind turbine, for example?
Yeah, you have a cutout velocity, I think, right, on these things to protect them. Yeah.
Correct, you do. So yeah, that is. It's always meters per second, so European units, but typically for a normal most turbines now are operate. They have a power curve that basically has a cut-in speed of about 4 meters a second, and if you double meters a second, you get miles an hour. Roughly, it's not exactly right, but so 4 meters a second, 8 miles an hour. If the wind's blowing faster than that, then the turbine starts to operate at that point. And as the wind speed increases from 3 or 4 meters a second up to about 12 meters per second, so up to about 25 miles an hour, then the turbine linearly increases the amount of power it produces with the wind. When you get to 12 meters a second, they then start pitching the blades such that it starts to take less energy out of the air than it could do, and you hold. For between 12 meters a second and 25 meters a second, the turbine will produce what's called its rated speed. So if it's a 14 megawatt turbine, it will produce 14 megawatts for wind strengths between 12 and 25 meters per second. And then if the wind speed goes beyond 25 meters a second, then the blades are feathered and the turbine shuts down because to protect the turbine, because the forces and the stresses on the structure are becoming too great. So that's the standard way all modern wind turbines pretty much will operate. But the structure is still there, even though it's not generating power, it's still getting battered by a hurricane. So but the OEMs of the wind turbines are convinced that they can design cost-effective turbines that would handle, in their shutdown form, but could handle hurricane conditions without routinely suffering major damage.
And I understand that there is an algorithm or computers that is actually turning it to get wind blowing into it more efficiently, normal times.
Yeah, correct. So
it could change. It could change its orientation in a bad situation by looking the other way, possibly.
Yeah, it can. Well, so they all clearly, if you think about one of the advantages of a vertical axis wind turbine is the wind can come at any direction and it's going to operate okay because because its axis is vertical. With a horizontal axis turbine, 3-bladed horizontal turbine, the turbine has to be able to yaw round so that it's always facing into wind. So you have a yaw control mechanism on it, which ensures that it's always facing into the wind. Interestingly, in fact, if because of that yaw mechanism, that what's called the nacelle, so the box on the top of the tower that the blades are attached to, all of that moves around, and that's where the generator is. And there's actually a power cable that hangs down inside the tower, which takes the power from the nacelle out through the side of the tower, and then along a subsea cable to the offshore substation where the outputs from all the turbines are joined together, so to speak. And if you think about if that turbine's yawing round, that cable, it's fixed at one end and attached to the rotating nacelle on the other end, so it's going to wind up. And so they actually they do unwind themselves as well occasionally. So sometimes sometimes you'll see the turbine rotating, not generating any power, but just rotating in order to keep the number of turns in the electricity cable at the correct amount. So yes, they all yaw so that they can follow the wind, but also, as you just alluded to there, they have algorithms for controlling the output, not of the individual turbines, but of the wind farm overall. Because when a turbine extracts some energy from the wind, there's a wake downstream of the turbine. And if that wake impacts upon the next turbine downstream, then it can reduce the amount of power that downstream turbine can generate. So if you try and optimize the output of the wind farm overall, you might choose to take less power out of the turbines on the leading edge, depending on which way the wind's blowing, so that you get more out, so that you get weaker wakes and more out the ones downstream. So that is certainly done either by either by pitch control of the blades so that you don't run them at the optimum angle, or you actually yaw the turbine a bit out of the wind to steer the wake away from the turbines downstream. Both of those methods work, and you can, we've done work on that here at Durham, and you can, it depends on the conditions, but you can get several percent additional electricity out the wind farm overall by optimizing the turbines at the farm level rather than at the individual turbine level.
It's sort of fleet optimization.
Yeah.
So I just want to touch on the policy. So in the report, they say, but just as important as delivering new secure energy, the sector now also supports 32,000 jobs, a figure set to grow to more than 100,000 by 2030. So this has become a major industry.
Absolutely,
hasn't it? Yeah.
And an industry, the life of a wind farm is 25 years plus. So and the government the UK government have a clear pipeline of projects that are being developed now. And one of those reports I shared with you really states is that there will be future leasing rounds as well, with large amounts of offshore wind. You mentioned them at the start there as well, to try and incentivize the developers and the supply chain in the UK to invest now for the good things that are coming in the future. So yeah, there's a huge number of jobs that come with this, and a huge number of challenges. If you're going to deploy the sort of scales of offshore wind that they're talking about in those reports, then we need more installation vessels for the turbines. We need improved port infrastructure as well, in order to, because even though they're offshore, they have to, the construction has to operate from a port where the bits are all stored and before they're transported out to sea. We need ports that are going to start operating like data centers almost, because there's huge amounts of data that comes back from these wind farms.
Performance and maintenance and
maintenance in particular, because when it's 100 miles offshore, okay, we will have, as the oil and gas industry has, we will have people permanently, well, not permanently, we'll have people stationed offshore for long periods, so that they don't have to travel the 100 miles to the wind farm every time a bit of maintenance is needed. But if it takes 8 hours to get 100 miles at least from a port, and then when you get there, you can only get on the turbine 30% of the time because the sea state is too rough the rest of the time. So so you don't, what you really want to be doing is scheduled maintenance, not unscheduled maintenance. So that's what the game is going to be all about. It's going to be about becoming much better at not measuring more on the turbines, but being more intelligent with the data that you use from that is already measured from the turbine. So an example,
AI might be helpful.
Definitely AI will play a role. So as an example, one of the things we worked on here recently was so there's an oil system within the nacelles that lubricate all the rotating parts. So obviously, as you can imagine, the rotor has a huge bearing on it, but there are gearboxes because the generator is rotating at a much higher speed than the rotor's going round. So you have gearboxes to step that up, etc. All of which require mechanical components to be lubricated. So there's an oil system within there, and we were looking at some more advanced oil conditioning monitoring instrumentation, and what that does was you can measure within the oil, you can measure particles, not only the size of them but also the number of them, so you get a measure of those two things. But then what do you do with that information? So if you're measuring away and you suddenly see a jump in the amount of particles that are in the oil, as for example, that can mean one of two things. It can mean something's failing, and what you're measuring is the metal that's spoiling off the failing component. Or it can mean that the whole turbine has just had a big jolt from a gust of wind, and all the crud that was in the bottom of the sump has gone into the oil, and it's all going around the oil system, but everything's fine. So it doesn't. So you need to look, as a very simplistic example, you need to look beyond just the oil signal at what else you're measuring on the turbine, in order to interpret more accurately what that information is telling you and what you need to do about it. So AI digital twins, etc., have a huge role to play in smart operations and maintenance systems, and there's a lot of work in that area at the moment.
I saw one other interesting thing, Simon. I want to get your perspective on this. So the fiber optic cables that connect this turbines in a wind farm. This research was saying it can pick up seismic activity and could provide sort of an early warning to impending seismic activity. Have you seen anything on that?
No, but I can well believe that is an entirely credible claim. Yeah, so the cables, there's an so obviously the turbines connect to the way it works is you might have 100 plus offshore wind turbines, and each of them will have a cable that runs to an offshore substation. So the substation then collects all of the power being generated by the turbines, and then there's a main transmission cable back to shore, or usually two, so there's a bit of redundancy if one gets damaged by a trawler or something like that, and that transmits the power back to shore when there's another substation there that then converts it to the right voltages and puts it onto the national grid. So that's how it works.
The step up is typically done onshore.
Yeah, because if you're going into the voltages are very high on the main national grid, much higher than they're transmitted back. But the cables, electricity cables, have fiber optics buried within them as well. So they are both an electricity cable, but they're also a communications cable, which is where this fiber. So they're all wrapped together in one bundle, and yeah, that the fiber optic is used for transmitting data back to shore, but there's lots of examples around where certainly with smart interrogation systems and sorts of things that have been developed, people find, well, actually, if there's seismic activity here, we can pick that up as well with this, just from the cable itself.
Yeah, so from the very little I know, Simon, this seems like the right technology. I saw some statistic that said if we harness available wind energy on the East Coast and the West Coast of the US, not even going into the Great Lakes, that can produce twice as much power that the US currently consumes. So available energy out there in offshore wind farms appear to be quite substantial, right? And
absolutely.
The question is maintenance. So where do we stand on that? I know that these things are rotating all day, and there's a bearings and all that stuff is going to get worn out, and then you need maintenance. So what is the percentage of maintenance cost in the total investment?
I don't. Difficult question to answer, really. So the maintenance costs are. But the best way I can answer it is you're always dealing anything in power generation, and wind farms are no exception to this. You're dealing with the difference between two very big numbers. Okay, so you have huge costs associated with procuring, building and commissioning the wind farm in the first place, and then huge costs associated with operating it for maintenance and what have you. But then the other column is the sale of the electricity. So the amount of electricity these things are generating, when you sell that's another huge cost. And obviously your profit is the difference between those two very big numbers. So, and obviously your capital costs are fixed when you develop the wind farm, and then your maintenance costs are so much per year beyond that. So I would guess, but it is a guess, that maybe the maintenance cost for 10 or 15 years is probably about the same as the capital cost when to actually build the thing in the first place. But that's a pure I don't know, that's a pure guess on my part. But that would sound like a sort of reasonable number. The big challenge, you're right that the wind resource is massive. The challenge is what we talked about earlier on. It's the fact that it's the variability of it, and the fact that it's only so you need
base load. You still need base load,
or storage. You can get away. You could get away without base load as long as you had large amounts of storage. Basically, you just want the power to be there when you need it, don't you? Or you want to incentivize your users called what's called demand side management. You want to incentivize your users to use the electricity when it's available, and use less of it when it's more challenging. So there are various schemes for smart
Dynamic pricing. Dynamic pricing is
yeah.
On the positive, though, this doesn't have spent fuel problem. So I'm not exactly sure the large nuclear power plants, when we think about cost, is that cost really factored in? I mean, say, well, I'm just going to put it in the wherever the spent fuel goes, and they will take care of it later.
No, I think the cost is factored in, and always in that industry, the volume of spent fuel is never as big as you think it is. It's not the huge. Don't ask me for numbers, all right? But I just know that it's always a shock when you learn physically how much of this stuff is there, and it's not the scale that you might imagine when you just think about it. So clearly that's the biggest challenge to do with nuclear fission. That you end up with depleted uranium or whatever, and you've got to store it somewhere for very, very long periods of time, and there's a huge cost associated with that.
I mean, the French should know all about it. 75% of their energy is coming from, I believe, nuclear, right?
Yeah, well, that's right. Well, that website, Gridwatch, that I mentioned to you at the start of this podcast, you can when you fire it up, you get the UK energy system, but there's a little French flag at the top of it, and if you click on that, you can see what France are doing. And okay. they are typically 70% plus nuclear. They're very proud of their nuclear fleets. The French. When I worked for Alstom, I once visited one of the French nuclear units at a place called Civaux, and I remember the plaque on the wall, and it said it was 110 meters from the end of the generator to the stop valves at the start of the generating set. So that's one turbo machine, everything bolted together on one shaft. I was stood at that and I thought, okay, it was pre-Usain Bolt, but I'll use Usain Bolt. It would take Usain Bolt more than 10 seconds to run from one end of this turbo machine to the other, and you could literally put your hand on the side of it when it was operating, and you could feel that you could have stood a coin on the turbine and it would have not fallen over. They are just incredible machines that they have there.
And they're advancing on fusion too, I think, right? So they have some sort of fusion facility that seems to get pretty close to production as well.
Yeah, there's a European project, ITER, or whatever it is called. That's a sort of European consortium project. Fusion is one of those things, isn't it? It's always 20 years away from commercialization.
Yes.
And I think they certainly are getting closer now. And so I think my personal view, I think it will be a reality. I think a decade from now, I think we'll have a much clearer and much more realistic view as to precisely when are we going to have our first commercial fusion reactor operating successfully. So and 10 years may I'm saying the picture will be much clearer in 10 years. That may sound a long way off, but it's not in energy terms. We're looking at offshore wind farm developments now 20 years out, what have you.
Yeah, I didn't know much about the wind arena, Simon. This seems like a really interesting area that countries should focus on. Some environmental issues, but then what energy? I mean, you don't get COPD by burning coal all day, and so you have to put. These are sort of competing technologies, so you have to compare the alternatives.
Yeah.
The thing about fusion, though, I don't know how you feel about this. It's concentrated production, so you still have transmission losses. Yeah. Unless we get room temperature superconductivity, you're still going to lose about 40-50% of it. So that is potentially an issue.
And I don't know though whether you could do the SMR equivalent, whether you could make small modular fusion reactors. I suspect that's credible, so you can distribute them to some extent in that way. But yeah, this is being clear about that sort of stuff is still, like I say, quite a few years off Yeah,
Few years off.
I
It
think.
has been few
Yeah,
years off,
yeah,
40 years now.
yeah. Well, and I know now, now
Yeah.
one of some of the latest advances has been what they call high temperature superconductors. But by high temperature, they mean 20 degrees centigrade above absolute zero. That's what they mean by high temperature in that
Yes.
in that case. So yeah, but you're right, they're all competing technologies. Some are much closer to commercial deployment than others. There are historical technologies such as the coal-fired plants that have been, certainly in the UK, being shut down now. If you're not in the UK, I mean, it doesn't rain here all the time, but it rains here quite a lot of the time. But if you are certainly in the more arid countries nearer the equator, then obviously the sun resource there is much greater than it is in the UK. We do have a lot of solar farms here in the UK, interestingly, as well. But in those sort of countries, it's much more likely that you would develop solar energy than wind energy, because that technology is getting cheaper and cheaper, and you see a lot of that happening. So it depends upon geographical location. And if you think about it, it's all of these things are a lot of them are just energy from the sun, isn't it? That's where all our energy comes from. So whether it's directly as solar, or whether the solar energy has produced winds, which we then extract with wind turbines, or whether the sun's energy has been used to grow biomass, and it's all energy from the sun at the end of the day, isn't it?
Yeah, if the sun doesn't come up
We're all
in the
trouble.
east, as they say, tomorrow, I think we are in trouble.
Yeah.
Excellent. Yeah. So let me just conclude with this, Simon. So 2030 complete decarbonization for UK. Do you think that's an achievable goal?
I think it's the right goal to have. I think achieving that by 2030 is going to be very, very difficult, mainly because of the things I alluded to a moment ago about the investment in port infrastructure, the investment in the vessels needed to construct the wind farms. Wind turbines are getting bigger and bigger and bigger, because that's the main reason that's been driving the cost down. But then your installation vessels need to get bigger and bigger and bigger. One of the consequences of going to deeper waters beyond 50 meters, there's quite a bit of the tower that's piled into the seabed. And installation vessels at the moment, the really big ones, can deal with towers up to around about 100 meters length. Bearing in mind a lot of that, some of it's got to protrude above the sea surface, some of it's got to go down. It's a little bit beyond 100 meters. But again, you need to develop new technologies, new vessels that are able to deal with installing, if you're still doing fixed bottom and not floating, installing wind turbines in much deeper water. So all of that needs to happen, and 2030 is not very far off. So
just 5 years away.
Yeah. So but the projects are happening right now. Demand will not be up at the 80 or 90 gigawatts for the UK that you read from that report at the start of this podcast. That because electrification of transport and of heating is also a challenge and won't have progressed at that rate. So we'll certainly have a lot more wind by then. Whether that's helping us to completely decarbonize at that point in time is if I'm honest with you, I'm not 100% confident that's gonna happen. But
it's a right path. It's a right path and the right goal to take.
Yeah.
And it's setting an example for many countries to study it, because you're also getting a lot of data, both on technology and implementation, maintenance, all sorts of things. So excellent, Simon.
That's really, for me, that's what the UK can offer to the world in this respect. We're not, as I said before, we're not the biggest country in the world at all. But what we can do is mobilize ourselves and try and exercise thought leadership and demonstrate to people that you really can do this stuff. And if you're prepared to make big decisions, like retire all your coal fleet, then like we did, then we end up where we are now, which I'm personally very proud of. I tell the students here at Durham that I've been in the energy business in one form or another for my whole career, and there has never been a time as exciting as now you know, it's happened at the wrong end of my career. There has never been a time as exciting as there is now to get into energy in one form or another globally. There's so much going on, and it's great for the, you know, to be here in the UK and for us to be in terms of deployment and demonstration at the forefront of that.
Excellent. Yeah, thanks so much for spending time with me, Simon.
Okay,
Really
well, thank
enjoyed it.
you. Thanks.
Thank you.